As you probably noticed, I did not post your quiz. Everybody notice that? Okay, I'm going to post it after class, and it'll be due, how about on Friday, since you guys have enough going on for Thursday. Okay. It will include this lecture, so it'll be up to this one, projections, and this one will pretty much is the bulk of it. Is everybody doing okay on your lab assignment? Yep. The uh-huh. Yep. Hmm. Something else? Uh-huh. Well, we can look at that. Is anybody else having a problem with it? I had to go through and download it again and start over with my joint too, so I don't know. Uh-huh. Okay. Well, we can look at that. Is anybody else having a similar problem? Michael? Uh-huh. Right. Remember, you have to call it a text. You have to make that GeoID column, you have to save it as text when you import it, and then it will retain the 0. Okay. Try that, and you can also go in and add the zeros back and see if that works. Sometimes it doesn't. If it's formatted as a number, it'll take the zeros away. But that trick was why you have to import it as a CSV in the first place. And make sure you delete that. Did you delete that extra row that has the second name? Yeah. Okay. Well, we can look at that after you guys are. No, you're bringing them in as an Excel. Yeah. Yeah. I think if you're bringing in, maybe for XY point data, you can bring it in as a CSV, but no, you're using Excel. It sounds like you're having something going on between your Excel and your ARC, so I don't know. I think I just need to look at that more closely. Okay, everybody else, it's there will be a reason why I will show you why I've asked you to do all of these separate processing steps on Thursday, because there are tricks. But there are reasons why you should learn some tools that will help you automate processes, right? I bet you guys are thinking about that already with all of the extraction steps we're going through. So, okay, everybody else okay? Anybody else need to? I can stay after class for about 15 minutes if you guys need more specific help. Okay. Okay, so today we're just going to go through some slides about what I'm referring to as the nature of geographic data, talk about data sources, and then actually just briefly about project design and management. So whenever we are going through this process of modeling the real world, as we're doing when we're building our GIS databases or mapping anything, it's important that we understand some aspects of the nature of geographic data, specifically thinking about things that phenomena that covary, things that we see covarying in the world, and thinking about how that variation changes with scale. And so those are some of the properties we're going to talk about. Specifically, we're going to look at spatial autocorrelation, to talk a little bit about self-similarity, and then how things are either smooth or irregular in nature. Again, covariation, how things vary. One phenomena varies with another, like how housing prices are going to vary, for instance, with proximity to roads or trains, or and then talk a little bit about how we need to think about scale. So geography, as a science, I think this is the only law of geography, which is kind of funny. Geographers have a complex about not creating enough laws. There's this big debate about whether geography is really a science, because science should be making laws. If you ever talk to geographers, you can ask them about that, and they'll probably respond. But this guy Tobler, this is the one law of geography we talk about, and it may seem sort of intuitive that everything is related to everything else, but near things are more related than distant things. And this is the essence of spatial autocorrelation. So when you're measuring two objects, if they're closer to one another, they're more likely to be related. There's more likely to be a correlation between those two than if they're farther apart. There are ways that we measure this phenomena, and it includes a measure of the similarity in location of objects as well as a similarity of their attributes. We don't need to worry about those mathematical measurements of it. What we need to know is that it happens, that when we're measuring things, when we're collecting data, that things that are closer to one another are more likely to be related and similar. The way we look at that is by how heterogeneous our things are in space. So this is just sort of an example of some spatial autocorrelation, where here we have the extreme example of extreme positive spatial autocorrelation, where all of the things are totally like each other when they're close to one another, versus the opposite here is extreme negative autocorrelation. So there's a pattern here, but you're not seeing that similarity between objects when they're close to one another. And it varies. It's along, there's a whole range. The other thing about it is that it depends upon how we measure it. So you can see that depending upon our sampling, we would have different values of our autocorrelation here. In general, all measurements are going to be spatially and temporally dependent. And so whenever we're thinking about autocorrelation, we need to think about what spatial scale and what temporal scale we're looking at. Another component of geographic phenomena is self-similarity. Fractals. If you've ever looked out a plane window and thought about how things vary on the landscape, you'll see there are just these repeating patterns that you find over and over again. This is just showing you another example in a fern versus that was one of those cauliflower broccaflowers. So whenever you are looking at things in nature, you need to think about the patterns that you're seeing and how they might be measured. So this is just talking a little bit about self-similarity and how we can measure that level of self-similarity. It's what we see in fractals, and it's what we see all the time repeated in nature. So here's another example where you have the self-similar structure repeating in like the mountains, the coastlines. And when we think about measurement of objects, especially measurement of like length in nature, it's something we need to think about. For instance, how long is the coast of Britain? It depends upon what scale we're going to measure it, how detailed we're going to be. If we're going to measure just the straight line across here, or are we going to go and measure every single turn of the coast? Maine, another great example of needing to think about how we're going to measure distance, showing that the different levels, the units that we're going to use, and how that's going to change our value. So these are things that we need to think about when we're building those models in GIS. How are the objects going to change that we're measuring depending upon the scale that we're using to measure them? Again, this is looking at a rocky coastline showing how you have these different repetitions and patterns between, like, say, your small rocks and your large rocks and the overall coastline pattern. That's just stuff that I think is particularly cool too. Fun to think about. So again, scale matters. If you'll remember from one of our earlier lectures, I talked about some of the different ways that we might refer to scale in GIS, in geography. These are some of these. Again, just that sometimes we talk about spatial resolution. Usually that's referring to, if we're in an image, our pixel size. When we talk about a fine-scaled resolution, we're having really small pixels. We're getting a lot of detail in our imagery. Versus coarse-scaled. You can also think about that with the measurement. That would be a fine-scaled measurement where you're taking very smaller units in your measurement. You're including those smaller objects. We talk about extent when we talk about scale in our map. Again, a little confusing because then when we're talking about a large scale, we're talking about a huge area. We're covering a larger geographic area versus small scale. Here we're talking about covering a small area. And then remember, map scale is another thing that we talk about, which is that representative fraction of the objects in our map and the objects in nature. Being specific about coarse versus fine can sometimes help you differentiate that better than small versus large. So the reason why we need to think about these properties of geographic phenomena is whenever we're developing data sets, we need to think about how we need to sample objects in nature. Geographic data are only going to be as good as the sampling scheme that we're using to create those data. So if we don't think about some of those properties, like spatial autocorrelation or what level of detail we need to use to measure something, we're not going to have very good data. And obviously, you guys are scientists, you know you can't measure everything in a population. You have to be selective about what you're going to measure. We don't need to because we have statistics to do that. But we need to think about how we're going to develop a good sample with all of these components of geographic information that we're talking about. Just some example of different spatial sampling designs that we might need to think about depending upon what pattern or what phenomena we're trying to measure. You guys are probably pretty familiar with sampling design. Is that right? You thought about it some? Or not? Take a research methods class? No? Maybe not. Nope. Archaeology. Yeah, you'd have to think about that a lot, about how you're going to design your samples there. So these are just sort of a range of different sampling designs that you might use depending upon what you're trying to measure. So like a simple random sample here is just showing you points that are randomly chosen from whatever the extent of your research area is. That can be good if you're just trying to capture totally random information about the landscape. Like if you're doing whenever we do an accuracy assessment of a map that we've created, we use a simple random sample. Well, I guess it's stratified because we do it per class, but then we choose random points across the landscape to really see if we're doing well. Versus a stratified sample where here you're using a regular interval. So if you needed to know how things were varying at specific distances across the landscape, you'd use C, for example, a stratified sample. If you needed to have some other component of randomness in your sample, but you need to be sure that you're getting your sample distributed well across your landscape, you would use, say, C, a stratified random sample. So you're sure you're getting good geographic distribution of your data, but there's no bias in your data that you're introducing. Sometimes clustered samples are better than randomly distributed samples. That can also be the case if it's really difficult to get to your data points. So if you're trying to get into the field to measure something, but it's going to take you 2 hours to get to each one of these different squares, and you have a limited amount of time, you can use some sort of a clustered sample too. Um, so this is just to show you guys some of the differences, different types of sampling schemes that are out there that you might want to think about when you're developing a data set. And some of the rules behind that, so the more heterogeneous your landscape, usually the larger a sample size you need. And landscape features, what's really on the ground, typically is going to be what's going to determine that sampling scheme. Like I was saying, if it's really hard to get into the middle of a dense forest, then you may have to think about what sampling scheme makes sense, or if you're working on a mountainside, or what things look like. And always, it's limited by reality. What are the resources? How much time and money do you have to spend on it? The other thing to think about is how do things, what's the relationship, like spatial autocorrelation, what's the relationship between those objects in your landscape? Based upon that, what kind of inference can we use to fill in the gaps between our observations? We use a lot of interpolation techniques in GIS. We have point samples, and then we need to fill in that whole landscape. And depending upon what we know about the spatial autocorrelation, or what we know about the landscape, is going to determine what kind of interpolation we are able to use. So just showing kind of an example of this. We're obviously going to need to think about our sampling and how we're going to fill in those gaps, what kind of interpolation we would use. In a landscape like this, it's going to be different than if you were in, say, the plains. So our sampling scheme and then the types of inference we're going to use with those samples are going to vary dependent upon what our landscape looks like. And we think about this in terms of distance decay and how the relationships between our samples are going to hold up as we move farther and farther away, farther and farther between our points. Frequently, we think about surfaces in an idealized way, like that movement in all directions is going to be equal. We call that an isotropic surface, that it's going to be uniform in all directions. But in reality, it's not. We have typically a very anisotropic surface where different directions is going to have different friction values. Things are going to change at different rates depending upon where we're going. And so we can measure how the relationship between our objects changes, or how our surface changes as we move through a measurement of distance decay. And the reason we need to think about that in GIS is, again, when we're going to model our surfaces, we need to know how our movement would be hindered depending upon which direction we're going in. So some maps that kind of illustrate some of these examples. So here is a map that's showing travel time to a doctor's surgery here in the middle of London. And because it's a very anisotropic surface, depending upon which direction we move in, what path we're able to take, they're not concentric circles, right? An isotropic surface where distance is going to be the same, take the same amount to travel in all directions, same amount of effort, would just be concentric circles moving outward. This is just showing, again, a different method actually of sampling, how we would use contour lines to fill in the relationship between all of our points, how we're going to fill in those unknown points. This is one time where they're saying, thinking about needing to measure spatial autocorrelation. You can see that there's clearly a pattern, a relationship going on between all of our samples. We need to know what the relationship is between our data points and how maybe these two objects that we're measuring here might be covariing. Here's another example where you're seeing that accident rates are going to be really different depending upon where you are in your network. Again, it's not a continuous surface where things are the same in all directions. This is showing a map of old people in southeastern England and how the distribution is not It's not uniform. It's going to vary. Showing volume data as another example. So how we need to think about our landscape and how things are changing inside of our landscape. Okay, so those are just some of the kind of basic background components that we can think about when we're thinking about developing sampling schemes and understanding for you guys to have some understanding of those concepts of spatial autocorrelation and distance decay and surfaces when you're thinking about developing sampling schemes for data. GIS data, your data collection is going to be sort of the core component of a lot of your GIS projects. Sometimes I'm just going to give you shape files and ask you to make some pretty maps with it, but when you go past that and you start thinking about how you would do some spatial analysis, what you're thinking about collecting to do your own GIS work, or how you're going to apply your GIS analysis to other work that you're doing, you have to think about your data. Because without data, it's just no fun. So we need to think about some things besides the nature of the data that we're working with, or what we're trying to collect, and how those are going to vary actually in the real world. We need to think about the quality of data and what kind of data can we use in our GIS. We need to evaluate our data before we start working with it, because there's a lot of bad data. There's more and more bad data all the time. So we need to think about how are we going to go about evaluating our data to know if it's good enough to work with. We're going to talk a little about where we can find data, and then how we might add data to our different ways we're going to add our data to our GIS project. So the more you work with data, the more you try and work with data in GIS, the more you're going to learn about it. But I'll try and impart some of this vast amount of knowledge that I have through these PowerPoint slides. Okay, so always in GIS, the question is, what do you need and what don't you need? Sometimes you can Google anything that you wanted to find data on. Maybe you guys were Googling where else you might be able to get population data besides having to go through the census process. And you'll find that there is a lot of data out there, but it's not always reliable. What should you leave behind? Oh, sorry, I thought I changed my order of slides here. Okay, so let's talk about this maybe before we get to the data sources. If we think about project management, and you guys should start thinking about what maybe you're interested in doing for your final projects. I don't know if anybody started thinking about that. I've been thinking a little bit about midterm project ideas. But the way you start a process of managing your work in GIS, especially when you get to start fresh and come up with your own ideas, think about what your interests are and what kind of project you might like to start working on. It might be something that you're already working on for your thesis or in your dissertation, and then you want to kind of pull out a little piece of it that you might be able to think about. So if you start most broadly, what are your interests, and then you start thinking about what kind of problem would I be able to solve with GIS? What might be a spatial problem that I can think about solving with GIS? And start thinking about questions and how you might approach them spatially. And then you need to think about what kind of methodology you're going to use to solve that problem. And frequently, it's good to kind of draw out a diagram of what process, a scheme of the process you're going to go through, your data collection, what kind of analysis you might be thinking about, what kind of end product you're hoping to get out of it. And then we have to go and think about finding what data we have, evaluating that data. We'll go through a process of writing a proposal. You guys will do this later in the semester, where you're going to specify what your objective is, tell me what your methods are, what data sources you found, and how you're thinking about going through that work. Then we'll go through our analysis and end up with our wonderful poster presentation of your results. So this is just kind of walking through what I was just talking about, how you're going to go about thinking about your data, your question, thinking about if that's a study area that you're specifically interested in, or what your question is, what are your data needs, looking and finding what data is available, and then going back and after assessing that, thinking more clearly perhaps about what you can actually get done for that project. Looking at your data after you've refined that question, thinking about if you need to go back again and reconsider your question based upon what data you have available. These are all sort of iterative questions and a process where you're going to go about kind of honing in on what you're able to actually do with what you have available, kind of refining that question. So once you go through the process of finding your data, doing your analysis, we're going to have our poster presentation. But down here at the bottom is kind of the most important step right now for you guys to think about. Always documenting your data sources. Always also document your processing steps. Where are you collecting your data from? How are you evaluating it? Are you having to do any processing with it? In the end, it's going to be a lot easier for you if you have that sort of sketched out, because you will forget. Okay, so there's a lot of different types of data sources that we can use. Frequently, you can get good data for free. Sometimes you have to pay for data, but more and more that's not the case. It used to be that we had to buy Landsat scenes, like satellite imagery, and now you can get as many as you want for free. So things change, but most of the time for you guys, all of the data that you will need will be freely available, or you'll think about collecting your own data. So broadly speaking, we talk about two different types of data: primary data, so data that you guys would collect or is directly collected, or secondary data, data that you're going to get from someone else. And as you already know, when we're working in GIS, we can work with spatial data, or we can also include attribute data that's not spatial. Okay, so the big difference between primary and secondary data. So with primary data, it's all the data that you or someone else, perhaps if you know directly, is collecting for you for a specific research project at hand. So when you go out and you're measuring trees, that's all primary data. Or if you're going out and you're taking GPS points, that's primary data. Secondary data is data that is one step removed from that. It's been gathered by somebody else for some other purpose. Maybe it's data that you're downloading. Different examples of primary data. This is just showing your a sampling scheme that was used. They're looking at the spatial distribution of some phenomena in a study area. So frequently for primary data, that's when you have to think about that sampling scheme. How are you going to go about collecting data to answer your specific research question? So this is showing that you could also, or mentioning that you can also do a sampling scheme from remotely sensed data. Like you could do collect data from imagery. That would still count as primary data because you are collecting this information about specific points. And always, as I mentioned earlier, that's when you really need to think about these things about how things are going to vary in your landscape. Think about what it is that you're trying to collect data on, and then developing your sampling scheme. So thinking about both the spatial component of your sampling scheme and the temporal. When we start thinking about imagery, we'll also think about the spectral resolution. So we can capture primary data in a number of different ways. We can do different types of surveying. You guys are not going to be doing surveying, but you might be recording locations with GPSs. Who's used a GPS? We're going to use that. Depends upon the weather, but we'll go out and we'll practice using GPS and collecting data and then importing it. so everyone can have more firsthand experience with that. But that's a lot of the way that you collect primary data. Sometimes you can also use sketch mapping to collect primary data if you're doing different studies about. For my dissertation work, I was thinking about how people use the landscape and then how the forest grows afterwards. So because it was a historical phenomena, the way the landscape had been used, we would use sketch mapping to draw out how, like, where people had been planting different crops, and that goes. Then you'd have to use digitizing of those maps. You have some GPS points, and you can also use interviewing to collect primary data. So back to GPSs. This is just an image of what the global navigation satellite system looks like. Hold on. So not only for our GPSs, but whenever we're using Google Maps to get anywhere using our navigation systems, we're relying on the global navigation satellite system. So there are a lot of satellites orbiting the Earth. And whenever we need to know where we are and we're going to use our GPS or we're going to use our phone or our navigation in our car, typically what happens is your unit, usually your GPS, is going to look for at least 3 different satellites. And using a triangulation method will know exactly where you are based upon your position relative to the 3 satellites. It is the most commonly used system for collecting any field data, our GPS data that we're going to input into our GIS. And again, it uses at least 3 different satellites to collect information on our location. The more we have, the more accurate our location will be. We'll talk more about this. The first ones were developed just by the Department of Defense. And then I think it was Clinton that finally released the higher level of accuracy of our GPS units. It used to be way back in like 2005 when I was first working on this stuff that you would never really know how accurate you were. You would always have like some unknown factor of maybe 10 meters that you could be off by. And it's just gone down and down and down as we've improved our accuracy. And now there's a whole bunch of different collections of these GNSSs that will give us information on our location. I was listening to NPR on the way over, and they was talking about how we're at this point where we have so much information accessible at our fingertips now that we're sort of ahead of ourselves in terms of controlling that and thinking about the security of things like this on the other side. I mean, there's some people who might say maybe it's not a good idea to know your exact location that's connected to your phone of all people. At any point you can be tracked, and not to get hyper paranoid about it, but there is sort of it's amazing how much more accurate these things are. We can know our location, but then there's another question of like, well, do we really want that information to be accessible to all people at all times? I don't know, something to think about. And something that it's just been such an explosion in how things have changed very, very quickly. Like, do you know that Samsung smart TVs that you can talk to apparently are also listening to you, and that you sign some sort of privacy. You say, okay, you can use that data however you want to. So, things to think about. Okay, so back to lecture. So we talk about different segments of our when we're using our GPS. There's the user segment. That's you. You've got your GPS. You're looking at the satellite segment, which is usually coming up showing you how many different satellites you can see. And then the control segment, which is the communication between the satellites and the ground, which is telling the ground where those different satellites are and doing the math. to tell you exactly where you are. So depending upon which GNS you're using, those are all going to vary a little bit, but that's broadly what it looks like. Okay, so now from hyper modern to maybe old school here. It used to be that all maps had to be digitized. There were, and there still are, these things called digitizing tables. And you would go and copy a map and all of the lines and features in the map by hand with one of these digitizers. And that's how the first maps were created. The first GIS maps. So when you're looking at old maps, it's always good to think about, well, how was this data created? Was it created like this? So people, and there's a lot of element of whoever's inputting the data and creating that map, there's going to be a huge range in quality of those maps. And now we still do digitizing. You guys will do some digitizing here. You can do on-screen digitizing. This is just showing Google Earth how you can actually go and digitize features by hand, create your own features. Field measurements, again, this is just showing much more accurate work with a survey crew trying to get locations more precise than what we typically worry about with our own GPS receivers. And then another source of primary data, imagery counts as primary data. So this is showing just one, I've shown you guys a lot of different images already, but this is just one image I'm not exactly sure what it's of, and then showing a satellite. I think this might be a Landsat satellite that takes imagery for it. Remote sensing is something we're going to talk more about, but just broadly speaking, we're taking, mostly we're using passive imagery, so we're capturing energy that's being reflected back from the Earth by our satellite sensor, recording that, and then distributing imagery. You typically are looking at one particular place when you're looking at satellite imagery, and we can look at that particular place and change over time, which is one of the most kind of powerful analysis tools that we really have. Looking at a huge record here going back from 1975 to 1992, which that was actually a long time ago now. But how we can study how, say, deforestation has changed the landscape. This is Rondonia. Landsat, the first Landsat images, the first really decent quality images. Sometimes you can get them in the 70s. Typically, it's more like the early 80s that you can start looking at a record. But it's pretty phenomenal seeing how things have changed. I'll show you guys some more resources where you can look at that over time. Now you don't have to do all the image classification yourself. They've got automated things where you can have, they'll show you how things have changed. Okay, so secondary data. Now this is important because you guys are going to be using a lot of secondary data. Probably more, right, than primary data, at least at this point. So secondary data, as we said, is anything that's been gathered by someone else for some other purpose, but you're going to use it for your own work. So this is just showing a map of how data availability can vary depending upon what you're trying to get. Typically, if you're working in the US, your data is going to be a lot easier to access. The distribution of data is there's so many different resources from the government, from the US government, the federal government, down to local governments. Everybody has their own GIS website now. So you can get all sorts of different data. If you're working in a different country, that becomes harder and harder. Sometimes it depends upon the country. Brazil has a lot of data available, but maybe Guyana, not so much data available. So it depends upon where you're working. And typically, the finer and more reliable your data, the harder it is to get as well as the more recent your data. So you can get census data. Historical census data is easier to get than the most recent census data, for example. Okay. You guys have any questions on this one? Pretty intuitive. But when you're thinking about a project, it's good to keep this in mind that some data can be harder for you to get access to, at least reliably. So there are so many different resources for you guys out there to get secondary data sources. This is just showing you a couple of examples. Like there's different GIS clearinghouses. Geodata.gov, that might need to be updated. Might be a new website now, but different. The USGS has a huge number of data sets. There's also private companies, but they'll typically charge you, and usually you don't have to do that. Usually you can find your own data in other places. Showing just some different data sources here. Also, Esri. Have you guys looked at the Esri website very much? If you go, when you go to add data, one of the, I think it's on the bottom, you can add data from Esri. If you click on that, you can go and explore all of the different things that they have available to you. Like you can get census data through Esri. I don't know if it's the 2010, it might be an older one. The census, we've already explored that quite a bit. USGS, that's the holder of all of the Landsat archive, a lot of satellite imagery, elevation data, soil data. There's a huge amount of data on USGS. Different street map data, engineering companies, and also different universities have different GIS data sources that typically are freely available to you. And just Google, there's a gazillion. So typically, you have to be thinking, you guys know how to Google stuff. Be as specific as possible when you're trying to find your data. Showing you a couple, these are all on the slides. So different GIS departments that have data that you might be interested in looking at. So this is, again, Esri. They have a huge amount of data available, and it's nice to use that because it's all ready to go. You can just load it. The Seamless server, if you're looking for data in the US, this is a good website to check out. You can see they have all of these different, they even have land cover data. There's a national land cover data set, so they map forest types or whatever the land cover is, or imagery, high resolution imagery. So I've just listed a bunch of stuff here for you guys to look at as you're trying to search out different data you might be trying to find. And this one, so for North Carolina, I wasn't giving you guys my data source yet because I didn't want you to download the data that was already in the right projection. But NC1Map it's the North Carolina clearinghouse for data. All of the data that you guys have in our mapping project so far has come from NC1Map. So I encourage you guys to kind of explore that and see what kind of data they have. I can show you that in a minute. Every county also has data. If you're looking for information on a specific property, Forsyth County, you can go and you can Google, you can add the property address and get information about that property. Everything's at your fingertips. Massachusetts, this is just to show you that I think every state probably has their own clearinghouse of GIS data. So depending upon where you're working, you might want to think about looking at that state clearinghouse because they typically have pretty high quality data. So you can go on and on and on. There's NatureServe. If you guys are working on thinking about a particular species that you're working on, has species distribution maps for different species that you can download. Climate data. I mean, it's awesome. So here we go, more data. Okay, but always think about the data quality of what you're working with. There are standards out there for how data should be collected, how it should be documented, but it is not always adhered to. Frequently, it's really not adhered to. I'm amazed sometimes by how little information comes with data. So you guys need to be prepared to evaluate the quality of data before you start working with it. And so in general, when you think about working with data, we need to think about broadly, what's the file format? Can I work with it? What scale is it at? How is it collected? How old is it? What are the attributes of it? All these things are the first thing. But then we need to think about this concept of metadata. Is there metadata associated with it? Do you guys know what metadata is? Metadata is data about data. So it's like, it's going to have all that information about how it was collected, who digitized that 1970s map of polygons. Without metadata, it's really difficult to work with data. You can try and figure that stuff out, but you can also make a lot of mistakes. Yeah. No, sometimes you can't, you know. Yeah. Yeah. I mean, if you had a choice between um, data with metadata and data without metadata, I would go with the data that has the metadata, but it's just not always there. Like having a shapefile that doesn't have any projection information attached to it. It happens. Esri will give you data like that sometimes, so it's really common. Um, Building up metadata and documenting everything is sort of the last thing that somebody's really thinking about doing. So, okay, so when you're evaluating that data, again, you have to think about the format that the data's in. Is it something that you're able to use? Is it a shapefile that you're going to be able to import right away into your ArcMap? That would be great. If not, is it in a different format that you can import, that you can do some sort of manipulation with it? If it's non-spatial, can you figure out how to use it? Are you able to get the information that you need? Is the attribute information what you really need, or is it a step away? Could you do some sort of transformation of it? Again, you guys know now the importance of having the spatial reference information captured. Is it defined? How about this one? Is it correct? I didn't try to fool you guys too much, but sometimes people have the wrong spatial information attached, and that's really when it gets confusing. Because not only do you not know that you don't know it's wrong, so you can have all sorts of other problems. It's another step. And also, does the spatial projection match the data that you're working? You guys remember topology? How the data was created? What are the rules about how lines meet up? Frequently, when you're working with data from different sources, you're going to end up with data that has all sorts of topological problems. So it's how you need to, before you start working with data, how you need to evaluate the quality of that data. Are you going to have to do a bunch of work to get it in the format that you can work with it? Questions about resolution? Remember, especially when we start thinking about satellite imagery or raster work, we have to think about the scale of our pixels. But also, remember that scale can also matter how data was created. Was it created at a fine enough scale? Were those polygons digitized at a fine enough scale for you to really work with, or are you going to have problems? Those are all things that you need to think about. And is the detail going to be enough? On the converse of that, could it be maybe too highly detailed? Sometimes you don't need high resolution imagery. Sometimes that's going to be more work for you to deal with than if you had coarser resolution. Always think about how recent your data are. Sometimes I mean, things are always being updated and improved, so always looking to make sure you have the most recent versions of things. If you're looking at some sort of change over time, are your time periods going to be frequent enough for your analysis? And always think about the sources of your data. How was it made? Who created it? And always, of course, copyright. Always cite your sources. Make sure that they're not copyrighted. Most data that you're able to get download, you don't have to. But I know, like, if you're using a Google Earth map in the background of something, you always need to cite that it's coming from Google Earth, for example. Okay, so metadata. How can we tell if we're really working with good data or crappy data? So in 1994, there was this statement about how digital data, how metadata should be collected, and that we need to label and document all of this explosion of spatial data. But as I mentioned, it just doesn't always happen. Frequently, you get data without any metadata. But it's really important for you to change that for you guys as you're creating data, to be sure to document where you're getting things from. And, inside of every shapefile, when you go under that properties button, there's a whole section where you can write in text about how you created your data, where it came from, any sort of processing you've done to it, and I highly encourage you to do that whenever you're creating shapefiles. It will give you, get you in a really good habit of documentation. So the problem really is that when we don't have data, when we don't have our metadata, we can misinterpret the data that we have. Maybe we won't know how accurate the data was. Maybe it was really old, or maybe somebody just made up data points and didn't try to get them really precise. So it's just really important to know what you're working with. Okay. So this is the stuff that we typically would like to have in our metadata. So all of the ID information, just the basic stuff. What is it called? What's the extent of it? What's the date? And then information about the quality of the data, the accuracy, where is it from, how is it produced, the spatial data, the reference information, if anything has been reprojected. As you guys remember, whenever you change the projection of your data, you're changing the underlying data and introducing some error. So if things have been reprojected, that's an important thing to add to metadata. And information about what it really is. What are we actually looking at? What are the attributes and what do they mean? And how things might be, if you had to get in touch with someone who had made the data, having contact information or distribution information is helpful too. Okay, so that's metadata. That's I'll stress metadata again. Always put information in your data that you're creating about what you've done to it. You do the change. Okay. So we've talked about a huge number of different data sources. I've shown you 8 million websites you can go to download data. I've told you about collecting GPS data. But there's also you have the ability to add your own data and import different types of data into GIS. So a lot of times now you don't actually have to go about doing much transformation because data is going to be readily available, especially working with Esri, with ArcMap. You guys know the shapefile is sort of the gold standard of how GIS files are shared. So you can typically just import things into ArcMap. But sometimes you have to go, especially when we start working with more imagery or working with data from different places, sometimes you have to go about sort of a process of problem solving to figure out how to import data into your work environment, into your GIS. All of our software programs, ArcMap, Idrizi, anyone, is going to have a huge host of options for importing data. So if I'm working in Idrizi, it's going to give me the option of importing shape files from ArcMath into Idrizi. So you can do that import between different software programs. But sometimes you'll end up with a strange file format, and you have to go about doing some research to figure out how to import it. We'll go through more sort of hands-on experience doing that a little bit later. But the trick is always identifying what the right importing tool is. Google is always helpful for when you're stuck with things like that. But you can also, as I mentioned earlier, you can digitize polygons. You can enter manually your own data. We'll work with that this week or next week when we do an editing lab, where I'll show you how to do hand digitizing and editing as well. You can also import your own XY coordinates. Like if you had an old file, or if you had a GPS points from someone else, you can manually import XY coordinates into your work as well. So whenever you're working with the digital data, you need to think about what the format of it is too. There's a lot of different formats. Typically, they're software specific. So when we're working with Esri, now you guys know the SHP, but there's also different different file extensions you might have depending upon the file format there. When we work with Idrizi, there's going to be a whole different set of file formats to get accustomed to. Different agencies also have their own file formats, Tiger files from the census. And then there's different ways that we go between data files. So this is just showing how we might export different files from ArcInfo, for example. When we work with images, there are going to be some standards that we'll get used to seeing. TIFFs. You guys are probably familiar with these just from images. And then there's a GeoTIFF, which is a TIFF that has geographic information encoded in it. So a lot of our Landsat images and such will be in GeoTIFFs. And then there's other ways. Different organizations, wherever you're downloading your data from, may compress your data differently too. So that's just about some of the things we'll get used to seeing, and as you guys are going about finding data, different things you need to get used to seeing and thinking about. Okay, so remember, as you're thinking about collecting data and as you're starting to think about projects, always document what you're doing. Write notes. Just start a Word doc or a WordPad and keep track of how where you're finding data from. If you're doing any transformation to it, it's just helpful in the long run when you go back and try and figure out where that file came from. What do those categories mean? Because it can get quite confusing. I'm going to show you guys some modeling tools, but this can be a helpful tool for you guys not only to automate processes, but also to remember all of the different geoprocessing steps we do is build models inside of GIS to keep track of all the things you're doing. Okay, and when we get closer, we'll start thinking about this more, but think about what your research questions might be, what you guys are interested in pursuing a little bit more, what kinds of spatial questions you might be thinking about. Have you guys started thinking about that at all? Yep. Good. Okay, and we'll talk more about that, but remember to look for as you're looking for data, think about metadata. Do the change. We'll go about this process too, but I mentioned you can add XY data whenever, if you have coordinates from other locations, you can add it into GIS. Okay. We'll go about that in this process. So this is just an example again of applications. Think about things you think about. Everything, for me, everything is a spatial problem. So climate change questions, species distribution. Okay, and this is just another slide for you guys as you're thinking about it. So think about how you're going to go about your process. So cool. Great. Okay, questions? Okay. So who has thought about project ideas? I know. Yeah, Sandy. Yeah, network analysis. Yes. Yeah, I don't know what license we have. We have different extensions. I know we have the spatial analyst extension. I think that there's enough network analysis in there. To look and make sure on that. Why are you thinking about something with network analysis? Yeah. Yeah. And how long? I mean, you have to. Is there a time component? Do you have to process it or? Yeah. Let's see. Network analyst. XTools Pro. Is that there's one that's free. Is that the non-free? Okay. No. Um, yeah, network analysts we don't have. We have 3D, which is kind of fun to play. I think we have spatial. Yeah, we have tracking. We don't have tracking. But we'll just I think we have 3. Not publisher. So that you want to buy them. Yeah, so we just have 3D and spatial analyst. I think that you can request a free trial of different ones. Does our book come with that 180-day free trial? I think it does. And if not, I have a bunch of different licenses that I could lend to you, and you can sign up and get them. Or you can just contact Esri directly and say you're taking a class and you want a free trial. And usually they'll give you like a 3-month license to try something out. So if you guys are thinking about something, I know you're thinking about some of the tracking stuff. So it'd be worthwhile. But as Jenny was saying, there's also different freeware add-on programs. So when you hit a wall with something and you want to be able to do something more sophisticated than what your basic license is going to allow you to do, sometimes people have add-ons for you. Sometimes they're good, sometimes they're bad. But we can talk more about that. But that sounds like a fun project. Do something with all that. Whoa. There's chicken. There are chicken farms like that out in the coast of North Carolina. They're smelly. They're a big waste producer. So yeah, if you can do something with the waste, that's really good. Chickens in the desert. Oh, let me show you guys this too. Add data from ArcGIS Online. I mentioned this to you before. So they have some stuff that we've gone to other places for, because it's good to know how to find it from other places, because it doesn't always work. But you can see population by zip code, federal land, better for U.S. data than for global data. Although I just saw that for South America and Western Europe, they now have the 30-meter SRTM data, which is big news because it used to be that you could only get that for the U.S. But if you go and you want to add something, it downloads it. And it gives you this error. So I'll figure out what that's doing. But the other thing that you have, which I really like, I think I tried to show you this guy before, is that you can add imagery or add other backgrounds. Of course, I don't have any data loaded that's going to add the whole globe, but it's actually pretty high quality imagery. So if we just want to zoom in here. And frequently it's nice to have some context for your data. Be warned though that it will slow your processing and display time down. So. It is. It's part of the Esri data. So under here, add base map. You can also add topography map. You can add street map. You can add just a nice light gray canvas background as well. So play around with that. So as you guys are starting to think about your questions for your research project, start Googling, start looking for data sources, and if you have questions, send them my way. But think about the quality of the data for sure. Okay, so if anybody has questions about that you want to ask me about your lab, I can hang out for a little while, and your quiz will be due on. Do you guys care if it's Friday morning or Friday night? Is Friday night? Okay, Friday by midnight. Okay, let me turn this guy off.